Hello there. Have you ever wondered why a playground swing doesn't keep going forever but swings back and forth smoothly until it stops? Well, today we are diving into the world of simple harmonic motion, or SHM for short, which is the secret behind many smooth, repetitive swings and oscillations. Here's a fun thought. Why did the pendulum break up with the clock? Because it felt things were just going in circles. Now, let's unwrap what SHM really means. Simple harmonic motion is a special kind of periodic motion that means it repeats itself over time. The key here is the restoring force, a force that always pulls or pushes the object back towards its central resting spot, called the mean position. Importantly, this restoring force is directly proportional to how far the object is displaced from that mean spot and is directed back toward it. We can express this neatly as F equals negative k times x, where F is the restoring force in newtons, k is a constant called the force constant, and x is the displacement in meters. That minus sign just tells us the force acts in the opposite direction to displacement. But it's not just force, the acceleration of the oscillating object also shares this relationship. The acceleration, a, equals negative omega squared times x, where omega, or omega, is the angular frequency measured in radians per second. So, like force, acceleration points back to equilibrium and scales with displacement. How do we describe the exact motion over time? That's where the general solution pops in. Displacement as a function of time, x of t, equals a times sine of omega times t plus phi. Here, a is the amplitude, the maximum distance from equilibrium, the omega we just talked about, and phi is called the phase constant, adjusting the starting point of the motion. Energy-wise, the story is just as elegant. Both kinetic and potential energy change sinusoidally through the oscillation, trading off back and forth, but their sum, the total mechanical energy, never changes. It's a perfect energy dance. If you look at the diagram on your slide, you see a smooth sine wave showing displacement oscillating over time around the equilibrium point. The highest points mark the amplitude, the farthest the object swings from rest. Understanding SHM is super important for everything from designing clocks to studying seismic waves. So next time you see a swing or feel your phone vibrate, remember the beautiful rules of simple harmonic motion at play. Welcome back. Continuing our journey into simple harmonic motion, let's take a closer look at how displacement, velocity, and acceleration change as the object oscillates. Imagine you're watching a mass on a spring moving back and forth smoothly. What are these quantities doing at each moment? We start with displacement. It's given by x of t equals a times cosine of omega times t plus phi. So displacement varies as a cosine wave, starting at some initial phase phi, which you can think of as the starting angle in our oscillation cycle. To find velocity, we take the derivative of displacement with respect to time, which simply means we see how fast the displacement is changing. The velocity, v of t, becomes negative a times omega times sine of omega times t plus phi. That negative sign tells us velocity points opposite to the sign of the phase. Similarly, for acceleration, we differentiate velocity once more with respect to time. The acceleration of t is then negative a times omega squared times cosine of omega times t plus phi. Notice that it equals negative omega squared times displacement, reinforcing the idea that acceleration always points back toward the mean position. What's really neat is what happens at the turning points, those moments when displacement hits plus or minus amplitude and the object momentarily stops changing position. Velocity is zero there because the object reverses direction, but acceleration is at its maximum, pulling it back. On your slide, you can picture these changes in the three-panel plot, One graph shows displacement versus time, the next velocity versus time, and the last acceleration versus time. The turning points and zero crossings are labeled so you can see exactly when velocity or acceleration hit zero or peak values. Understanding this relationship helps engineers design systems like shock absorbers and seismographs where control oscillations are crucial. So the next time you watch a clock's pendulum swing, think about how displacement, velocity, and acceleration are all dancing together in perfect, rhythmic harmony. Hello again. One of the most magical things about simple harmonic motion is how energy keeps shuffling back and forth in the system without ever disappearing, at least in an ideal world without friction. Let's explore this exchange between kinetic and potential energy. The total mechanical energy, E, in SHM remains constant through an oscillation. It equals 1/2 times k times a squared, or equivalently 1/2 times m times omega squared times a squared. Here, k is the stiffness of the system in newtons per meter, m is mass in kilograms, omega is angular frequency in radians per second, and a is amplitude in meters. So, the total energy depends on how stiff the system is, how heavy the mass is, and how far it swings. Potential energy, U, changes as 1/2 times k times x squared, where x is the displacement at that instant. This means potential energy is highest when the object is at its maximum displacement plus or minus a and 0 at the equilibrium. On the flip side, kinetic energy, the energy of movement denoted k, is 1/2 times m times v squared, or 1/2 times m times omega squared times open bracket a squared minus x squared close bracket. This tells us kinetic energy is 0 at the extremes and hits its maximum at equilibrium, where speed peaks. So if you imagine the mass moving through its path, energy shifts gracefully between kinetic and potential forms, but the total energy stays the same. The plot on your slide shows energy on the vertical axis and displacement on the horizontal, with curves for kinetic energy, potential energy, and the constant total energy line. This concept is everywhere, from how bridges flex under wind loads to how atoms vibrate in a crystal lattice. So the energy story in SHM is a perfect example of physics elegance and balance in action. Welcome back. Now that we know how the object's position moves back and forth, let's talk about timing and phase, the rhythm and timing of this oscillating dance. The phase, theta, equals omega times t plus phi, and it's the angle or state that tells us exactly where in its cycle the motion is at any given instant. Think of it as the clock hand on a circular dial telling us the precise moment in the oscillation. The time period, t, is the duration for one full oscillation, from a starting point back to the same spot going the same direction. Mathematically, time period is 2 pi divided by omega. So, if you know the angular frequency, you can find how long it takes for one complete oscillation in seconds. Frequency, F, complements this by telling you how many oscillations happen each second. It's 1 over t or omega over 2 pi, measured in hertz. Here comes a fascinating analogy. Simple harmonic motion can be imagined as the shadow, or projection, of uniform circular motion onto a line. Picture a point moving in a perfect circle at constant speed. If you watch only its shadow oscillating left and right on a horizontal line, that shadow follows simple harmonic motion. The diagram on your slide shows this clearly, with the circular motion above and its linear projection below, mapped as a function of angular coordinate to linear displacement. This analogy helps us connect rotations and oscillations and find elegant ways to analyze waves and vibrations. From the swinging of a child's swing to the vibrations inside musical instruments, understanding phase and time period helps us predict and harness oscillatory motion with precision. Hello physics fans! Let's zoom into one of the classic examples of simple harmonic motion, the mass spring system. Imagine a block attached to a spring hanging vertically or resting horizontally. When displaced, the spring exerts a restoring force pulling it back. Mathematically, this restoring force equals negative k times x, where k is the spring constant in newtons per meter and x is the displacement from equilibrium in meters. This force leads us to the equation governing motion. Mass times the second derivative of displacement with respect to time equals negative k times x. In simpler words, mass times acceleration equals the restoring force, Newton's second law applied to oscillations. From here, we find the angular frequency omega equals square root of k over m, measured in radians per second. This frequency dictates how fast the mass oscillates back and forth. The time period t, the time it takes for one complete oscillation, is 2 pi times square root of m over k, measured in seconds. Notice it depends on mass and spring stiffness but not on amplitude, which is pretty neat. This basic model assumes no energy loss due to friction or air resistance, an idealized but very useful starting point. The diagram on your slide shows the mass hanging on the spring, with labels marking the equilibrium position and amplitude displacement, and a graph of vertical displacement versus time showing the smooth oscillation. Mass spring oscillators are everywhere, from car suspensions keeping your ride smooth to measuring tiny forces in labs. Understanding their motion is fundamental to both classical and modern physics. Hello again! Another superstar of simple harmonic motion is the simple pendulum, the classic weight suspended on a string swinging back and forth. Here, the restoring torque, or rotational force, is given by tau equals negative m times g times L times sine theta. Here, m is mass in kilograms, g is acceleration due to gravity in meters per second squared, L is the length of the pendulum in meters, and theta is the angular displacement in radians. For small angles, usually below about 10 degrees, we can approximate sine theta as just theta itself in radians. This simplifies the math drastically, reducing the equation to the second derivative of theta with respect to time plus g over L times theta equals 0, clearly showing SHM behavior. The angular frequency omega then becomes square root of g over L, measured in radians per second, showing that it depends only on the pendulum's length and gravity, but not on mass. This independence on mass is why pendulum clocks keep such accurate time regardless of the bob's weight. The time period t, the time for a full swing back and forth, equals to pi times square root of L over g, measured in seconds. The diagram illustrates the pendulum swinging, with labels showing the mean or equilibrium position and maximum angular deflections on either side, along with a plot of angular displacement versus time. Simple pendulums are more than just classroom toys. They show up in seismometers, grandfather clocks, and even in understanding Earth's interior through oscillations caused by earthquakes. So, swinging into SHM with pendulums bridges practical timekeeping and fundamental physics beautifully. Alright, time for some practice magic. Imagine we have a mass of 0.5 kilograms attached to a spring with a spring constant K of 200 newtons per meter. We want to find the displacement as a function of time. We start by using the formula for simple harmonic motion displacement, x of t equals a times cosine of omega times t plus phi, where omega is the square root of k over m. Plugging in our numbers, omega becomes square root of 200 divided by 0.5, which simplifies to 20 radians per second. Let's say the amplitude a is 0.1 meters and the initial phase phi is 0 for simplicity. So, our displacement equation becomes x of t equals 0.1 times cosine of 20 times t. This tells us that the object oscillates between plus and minus 0.1 meters, with 20 oscillations happening every second in terms of angular displacement movement. The resulting plot on your slide shows displacement versus time, with clear markers at t equals 0 and max and min amplitudes, illustrating this sinusoidal oscillation. This example confirms how mass and spring stiffness determine how fast and how far the oscillations happen, a practical application of the theory we learned. Remember, these results are idealized and assume no damping or friction slowing the oscillation. Mastering such calculations helps engineers design everything from vehicle suspensions to measuring devices accurately. So, to sum it all up, simple harmonic motion is best described by displacement as a function of time equal to amplitude times cosine of omega times t plus phi, where each symbol has its important role. Velocity follows as negative amplitude times omega times sine of omega t plus phi, and acceleration is negative omega squared times the displacement, always pulling the object back to equilibrium. The total energy remains constant at 1/2 k times amplitude squared, oscillating between kinetic and potential forms. SHM arises due to linear restoring forces near equilibrium, and its beautiful sinusoidal variations in displacement, velocity, and acceleration define this motion. Both pendulums and mass spring systems model SHM, with time periods depending on system parameters like mass, length, and spring stiffness. From playground swings to clocks to seismic waves, understanding these principles shows us the rhythmic heartbeat of the physical world. That is it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.